Live. Okay, we're good. That is fancy. Okay, sorry about being late. I apologize. Thank you for turning those in. Thank you for sending me the pictures. Someone requested that I post my favorite. So as long as that person is okay with it, I will show that person's picture when the time comes. Okay, so I was looking at my notes. I was like, well, I have a lot to say today. Surely I didn't get through this in the last time I taught this course, and it turns out I got through all of it. So I have to get through like 9 pages of notes today. So, no questions, no clarifying questions. You're not allowed to say anything. You're not allowed to slow me down at all. If something is confusing, tough. Suck it up. No, I'm kidding. You should obviously ask questions. Okay, so today is when shit gets real. We're going to get into some math that many of you might or might not have seen before. Quite a bit of what I'm going to develop today is fortunately also very useful in the context of particle physics, and for those who have studied particle physics or taken my class will recognize things that they've seen before. And a lot of that has to do with the fact that we're going to make use of symmetry in getting started with the course. So I'm going to start with a couple of statements and words about relativity and symmetry. So let's start with a statement about relativity and what it means to have some kind of principle of relativity. And in words, we can say the laws of physics should take the same form to all inertial observers. Okay? And this is a relativity principle which actually underlies both special relativity, but also Galilean relativity, the older relativity that is relevant when you're just using good old Newton's law in Physics 1. And so you might kind of wonder, well, what's the difference between those two? Well, it's not just relativity, but we also have to talk about symmetry a little bit. And there are 3 symmetries of space and time which are relevant for both Galilean and special relativity. First, we have the isotropy of space. Can anybody guess? And by the way, thank you for sending me the cards, but I chose to go to colloquium instead of creating the deck of cards today. And so I will have those on hand for Thursday. And so I promise, Adria, you'll be the first card that's drawn. But good. Well, since we're on that subject, Adria, what do you think is meant by the isotropy of space? So what does the word isotropic mean to you?
It means no heat is?
So, no. So there's a lot of parts of this word that are akin to things that you've seen in thermal physics and thermodynamics, so that's kind of understandable, but go ahead. I think you got to phone a friend back there.
Oh, yeah.
Mike.
Like an orderliness of space, like a homogeneity throughout?
Well, you got to be a little bit careful. It definitely has to do with orderliness. So isotropy is associated with the idea that if you stand in one place and you look in any direction, everything looks the same. Okay? That's actually not technically the same as homogeneity. Because you could imagine that if the Earth was, or if the universe was sort of spherically symmetric, just spherically symmetric, and you happen to be at the center, and you look around, everything looks the same. But if you're not at the center, everything doesn't look the same. Does that make sense? Okay. So isotropy is basically you rotate things and nothing changes. So for example, we can have a little physics lab. And I have to stress, we tend to think of a lot of these definitions as being applied to like the physics lab in this building. And the truth is that's not where we're setting down these sort of fundamental ideas about the symmetries of space and time. Let's, to be clear, imagine we are in the deepest of deep space. There's absolutely nothing around. and then you have this floating laboratory and you do an experiment, okay? Isotropy of space means if you take the laboratory and you rotate it any way you want and then do the experiment again, you'll get the exact same results. That's all it means. Clearly that does not happen on the surface of the Earth, because if I take a lab and I throw a ball this way, it'll do something, and if I take the lab and rotate it and I throw the ball this way, in this room, it will do something different, okay? But that's because the presence of the Earth breaks that isotropy. So then we have the homogeneity of space, which you were starting to allude to. And can anybody take a guess as to what homogeneity of space would describe?
You can move your lab anywhere in space and everything's the same.
Exactly. I can move my lab from one point to another, do the experiment here, move over here, do the experiment, everything's the same. So I can translate in space and nothing changes. Okay? And the last part is actually homogeneity in time. And I think that's fairly obvious. As an extension, I can translate in time and nothing changes. Okay, so I can do the experiment now, wait 10 minutes, do the experiment again. I should get the exact same result. The physics should be unchanged. Okay? Both of Galilean relativity and special relativity, and I guess I should sort of just even pause for a minute. There were maybe a couple of words that I meant to say or that I didn't get to on the last page of notes from the last lecture. And that is, this is a class in general relativity, but we are going to start with a very careful in-depth look at special relativity. And there's a couple of reasons for that. Number one, I need to undo all of the wrong that was done or is going to be done to you in modern physics, where you learn to hate special relativity because it's very confusing. I need to convince you that special relativity is very beautiful and way more straightforward than it might have seemed. Secondly, in developing special relativity for reals, we're going to develop a lot of technology which directly translates into general relativity. Okay? And in a very, very deep sense, there is a connection between special relativity and actually formulating the theory of general relativity in terms of the fundamental principle on which you formulate the theory. And so it really, really pays off a lot to spend time getting really, really comfortable with special relativity, but not in a way that you've probably seen it, at least in your modern physics class. It's going to look a little bit different. This principle of relativity and these symmetry observations are shared between Galilean and special relativity. And so you might ask, well, what the hell's the difference? Does somebody want to ask that?
What the hell's the difference?
Well, let me tell you what the difference is, and I would just appreciate it if you would not curse.
My apologies.
Okay. All right. So if we're talking about Galilean / sort of Newtonian ideas of relativity, in that framework, they held to the idea of what is called absolute time. They held to the tenet that everyone must agree on, for example, the time interval between two events. Okay? So, for example, everyone must agree on your age. That's the two events of your birth and your current existence. Okay? Everyone in the universe, no matter where they are, what state of motion they're in, okay, if they're moving with respect to you or not, the notion of absolute time is that everyone agrees that the time interval of 10 seconds is the time interval of 10 seconds. I mean the time interval of 10 seconds between two events. Okay, that will be a 10-second time interval no matter who measures it, no matter their state of motion. Einstein, on the other hand, took a different thing that he held near and dear and is inflexible. And that is that Einstein said, actually, no, the thing that I want everybody to agree on is the speed of light. I think that everyone should record the exact same value for the speed of light, no matter what their state of motion is. I can turn a flashlight on, shine it into my face, and I'll measure c. I can take the flashlight and shove it into my face, and I'll still measure c, which is not what we expect with Galilean relativity. You would add those two velocities. Now, it turns out these two things are incompatible. You can't have your cake and eat it too. You either have to agree with absolute time or the constancy of the speed of light. Well, a lot of physicists for a long time had a really good reason to think about absolute time. Nobody was seeing anything that was suggesting that time intervals between events were different for different observers. You might wonder why Einstein was so ready to give it up. Well, it turns out that measuring the constancy of the speed of light for different observers is actually a little bit more straightforward than doing this. So there was experimental evidence that amounted to everybody sees the same value of C. This, of course, the famous Michelson-Morley experiment. But then you also have C arising in another fundamental theory, and that's electromagnetism, where you get the wave propagation speed of light irrespective of the state of motion of the observer. So there was actually a lot of good reason to accept this, but he just realized that that was going to have to be at the expense of this. Okay? And he was willing to take that step, and he did it. Now, by the way, someone probably should have asked me last time, and I'll forgive you for not. I was making this big hoity-toity discrepancy between what I called a framework, where you were talking about a context in which you do physics. So we had like Newtonian physics and quantum mechanics and special relativity and quantum field theory. And then I separated that from the notion of a theory where you take particular forces and stuff and you work with them in a particular context. And I argued to you, general relativity is a theory. It's the theory of gravity, okay? And it's done in the context of special relativity. But I want to pose a question. Who wants to be the sucker that has to answer it? Okay, you're up. If special relativity is a framework that's not tied to any particular forces, right? You can do any force you want in special relativity. Why is it that light plays such an important role in special relativity? After all, it is the ultimate speed. Ooh, this is what the deck of cards would do. No, I'm just kidding. This is actually a hard question. Anybody? Any takers?
Is it because it's massless?
Exactly. It's not that light is the special thing. It's that something that's massless is special. Anything that's massless travels at the speed of light. We should really call it the speed of masslessness, and then light is an example. It's just that at that time, light was the only thing around that we, understood to be massless. Okay? So this is one of the, initial early confusions with relativity. This speed is really a fundamental speed associated to anything that is massless. It's not that light plays a particularly special role in defining special relativity. It's the speed of masslessness that does. And that can be appropriate no matter what force you're talking about. Okay? All right. Now, if so this is sort of the distinction in sort of the bedrock idea that gets you to Galilean relativity versus special relativity. We're, of course, going to spend a lot of time talking about the results in the framework here. And much, much later on, in like 3 or 4 lectures, I'm actually going to come back and show you what this looks like. And what you're going to realize, funnily enough, is that this is actually way more complicated than this. This is actually beautiful. This is fugly. Okay? And the reason that this is so beautiful is just a consequence of the symmetry that is forced on you by this one particular addition to this story. And the symmetry that is forced on you is that the isotropy of space is expanded to not just the isotropy of space, but the isotropy of space-time. And what we find is that much of special relativity is really just a study of rotations in 4 dimensions. In the same way that when we think about isotropy of space, we talk about rotations in 3 dimensions. Okay? So what we're going to do today is we're going to sort of get a mathematical formalism for talking about these things. All right? And then what I guarantee you that I'm going to lose some of you. There's going to be a lot of sort of formal stuff written down. And that's okay, because the next lecture is going to be 2 concrete examples of applying everything I talk about today. So I just want to get it on the table, you can mull it over for Wednesday, and then on Thursday we'll come back and we'll just look at it in a very concrete setting, and I think that'll make you more comfortable with a lot of the things I say today. Before I erase all this, are there any questions? Yeah.
So when you say isotropy with time,
Isotropy of space-time.
okay.
So that basically it means, so when we talk about isotropy of space, we talk about rotating. Basically, when we rotate, we kind of mix x and y and z. Here, we're going to allow the mixing of x, y, z, and t.
I just think in terms of time, you're always kind of looking in the same direction, because there's only one direction in time.
So that's actually got more, that's got a slightly separate, okay, so there is a notion that we're going to develop in the context of special relativity that is it's a parallel of a notion that we develop here, but we have to develop it in a different way, and that is the notion of causality, which is basically writing down, you know, what in our space-time determines the possible relation of cause and effect. And that is going to play into this role that you only move forward in one particular direction. So yes, putting causality on top of it kind of destroys the perfect isotropy, but we're not there yet. We're not talking about causality yet. That'll come a little bit later down the road. Okay. The questions? Okay. All right. So, we should ask ourselves, if I say that the physics looks the same to all inertial observers, what exactly do I mean by the physics looks the same? So when we say, you know, what is our physics? What is the thing we're doing? You know, back in your first physics class, you would say, oh, I've got F equals ma. That tells me how forces create accelerations of things. And then I've got force equations, you know, so you can talk about, you know, if you're talking about the force on a charged particle in an electric field, you might say, oh, if I've got a charged Q in an electric field, I multiply those 2 things together, that tells me the force the particle feels. I take that force, I plug it into Newton's second law, and now I can predict what the particle does. That's the program of solving problems in physics. You have influences, and then you want to use those in some model to predict behavior. This is not really a great way to deal with things. We need to be a little bit more sophisticated. This is really just one example of many different things you could ultimately arrive at. And so the more sort of holistic way that I like to refer to writing down physics is to basically construct an action. And in non-relativistic physics, the action is the integral of a Lagrangian with respect to time. And in four-dimensional relativistic physics, it is the integral of a Lagrangian density with respect to all 4 coordinates of space-time. So this is the kind of expression you would use if you were doing quantum field theory, if you're doing general relativity. This is something that you beat the hell out of in 350. Some people in the room don't know what Lagrangians are. That's okay. We're not really going to work directly with Lagrangians. What you need to know about them are the following. A Lagrangian, at least in this case many people in the room don't really know about, so don't worry about it. A Lagrangian in the simplest context is literally built out of kinetic energy minus potential energy. So Lagrangians are very similar to energies. And just like energies that we're familiar with, they are scalars in space-time. Okay? They don't have direction. Okay, so Physics 1 students love that about energy. I don't have to deal with vectors. So you think, till you see a line integral. So literally when you see L, and when I talk about L, you can just kind of use that as a proxy for things like energies. What's important about this is that if I say the laws of physics are unchanged, that means that if I write down the action for that I'm going to use to describe the results of an experiment, and then I consider doing the experiment over here, so that's a translation, and I write down the action to describe it over here, the action I write down over here looks identical to the action I wrote down over here. So that's what these symmetries mean. It means that the action doesn't change when you affect these transformations. Okay? So whatever expression you end up writing down, If you ask what would it look like if I translated it or rotated it, it should actually end up looking exactly the same. So we're looking for invariances of the action. Now that gets really confusing because invariance of an action leads to a notion, and I'll talk more about this in detail later, of the covariance of the equations of motion. So the statement is that the equations of motion are, it depends on the level at which you're talking about it, but the equations of motion are not necessarily invariant. It's the action that's invariant, and the equations of motion in turn end up being what we call covariant. And I'll talk more about what that means when we actually start writing down equations of motion. And for anyone who's scared of the notion of equations of motion, you've been working with one since week 2 of Physics 1. Newton's law is an equation of motion. Okay? All right, so here we go. The goal here now is to focus really hard and heavy on symmetry, to get a mathematical description of symmetry, because we're going to find that we can very, very concisely state pretty much everything in special relativity in terms of a single symmetry statement. That'll be a little bit down the road, so we got to build up the tools to get there, okay? And again, everything I'm about to say for today and largely for tomorrow is exactly analogous to what we would do if you were studying particle physics. So symmetry is incredibly powerful. You know, one of the first places you saw symmetry was in looking at problems and trying to make them easier to solve, right? You know, if you have some potential, which is just some crazy function that has no regularity, you know, solving the motion of a particle in that potential can be crazy, but then if I say I'm going to make it spherically symmetric, then you're like, yes, that's so much easier. Or better still, I'm just going to make it completely uniform. That's a super easy problem to solve. Nothing interesting happens, but it's an easy problem to solve, so you got to pick your battles. However, I want to convey to you that in addition to making things simple to solve and pretty to look at, we all want to be pretty, symmetry actually plays an incredibly fundamental role in physics. And those who study particle physics know this. At the heart of each and every interaction in nature, that's the gravitational, the strong force, the weak force, and the electromagnetic force, at the heart of all of those is a statement about symmetry. Those forces are built and based fundamentally on a symmetry statement. And the tools we're about to describe, for the most part, can be applied to all of those forces. So we're going to talk about symmetry. And the first type of symmetry I'm going to talk about, which is what you're most familiar with, is an example of what I might call a static symmetry. And a static symmetry, and I'm going to talk a lot about static symmetries because they're the kind that we can draw. And the first thing I have to do is actually draw something symmetric. Oh God, this is so stressful. That's not symmetric either. But let's pretend that's an equilateral triangle. And one of the things that we know is if I take an equilateral triangle and I rotate it through an axis going through the center by 120 degrees, I end up with the same picture, right? That's the beauty of an equilateral triangle. And I can rotate it to 120, 240, and then again getting back to 360. That's a symmetry you can stare at, see, move with your hand. Oh, it looks the same. Wow. That's what we call a static symmetry, okay? Those are not the symmetries that we're going to deal with in this class. But we can use these symmetries to develop the math tools that we're going to need. What we're really interested in is dynamical symmetries. And the dynamical symmetries are where we take, for example, the Lagrangian that we use to define a physical theory, which is not shapes. It would be cool if you could work out a mechanics problem, you know, where your Lagrangian was this, but I don't know how to work with that very good. So we know what goes in Lagrangians. It's like functions and derivatives of functions and all that kind of crap. But if we take our Lagrangian and we transform it, the analog of rotating a triangle, we ostensibly get some new Lagrangian. If it's a symmetry, though, that should look like the original Lagrangian. Technically, we should be talking about the action, but I'll use them interchangeably, action and Lagrangian, at this level of discussion. If you're confused about the difference, talk to Brad. Okay. So, implicit in both of these, as sort of a starting point to the discussion, is that we're transforming something. We've got something and we're going to do something to it. Second to that in the story is that after you do the thing, it looks the same. That's invariance. So what we're going to spend our time developing right now is a mathematical theory of transforming things. And then we'll finish up today with talking about, okay, we know how to transform things. How do we get invariance? How do we make things look the same after the transformation? Okay? So we're going to spend quite a bit of time right now talking about transforming. And, yeah, okay. So, the mathematical theory of transformations. There are a lot of words that come with describing transformations in physics. Here's a laundry list. Oh my God, that's a long list. Finite, infinite. Like an infinite list is what it is. Compact, NonCompact. It just goes on and on.
So
Internal, space-time. Okay, so that's kind of a reasonably exhaustive list of the various kinds of adjectives describing transformations in physics. Let's go through them all, one by one.
goody.
Ready? So let's start with the idea of global versus local. Okay. So in this case, I'm going to consider a system. And again, I am going to use static examples, things I can draw and you can look at, as opposed to functions and Lagrangians right now. Because if we get the definitions down, we can apply it to both. Okay? These are just easier to picture. So the system I'm going to consider is an array of dots. Okay? And the transformation that I'm going to consider is a translation of the dots. Okay, that is the thing I'm allowed to do, is to take the dots and translate them. Okay? So we can imagine what we might mean by a global transformation of this sort. That is, we take all of the dots and we uniformly translate them. So afterwards, we might get something that looks like this. That is, we preserve the sort of shape of the array. We just take the whole thing and dislocate it. A local version of that transformation means that I can take each dot and translate it differently. And of course, as you're probably aware, if I do that, then the only thing I'm sure of is at the end of it, I'll have 9 dots. But there is no reason to expect that they will end up in that nice symmetric array that I started with. Okay? So the word global, when we talk about transformations, means we're doing the same transformation on each element of our system. A local transformation means we can take each thing and we can do the transformation differently. All right? Now this is kind of cool because if you look at this guy, you would say this is symmetric. Under global transformations, the shape is the same. This is not symmetric. Obviously, the shape has changed. So you might wonder to yourself, well, when the hell could you ever get something that was symmetric under a local transformation? Let me show you an example. So our second example, our system, is going to be, just to make it simple, 4 circles. And our transformation is going to be rotations through the center of each. Okay? So of course a global form of that would be to take each and every one of these circles and rotate them by, say, pi degrees through their centers. But you all know what you end up with. You end up with a picture that looks exactly like what you started with. A local version of it would be maybe take this one and rotate it pi over 4, take this one and rotate it pi, take this one and do nothing to it, and then take this one and rotate it through 3 pi over 4. But you know what you get. You get the exact same picture. So it is perfectly reasonable to have things which are invariant under local symmetries, where you're actually doing a different transformation on different parts of the system. Okay. These local transformations end up playing a very, very crucial role in how symmetries define physical theories. We're going to see that in general relativity, and it plays a very, very important role in particle physics. The global transformations play an important role as well, but in terms of defining forces, it's the local transformations that are really key. So we got 2 of these words down. One observation we can immediately make from this is that if I have a theory which is invariant, or if I have a system which is invariant under local transformations, so if the system doesn't change when I do it differently at different points, then it is automatically invariant under global ones. Because if I can do things differently on different elements and it doesn't change, I can certainly do the same thing to every element and it won't change. So local implies global, but not vice versa. Okay? All right, discrete versus continuous. This one's pretty straightforward. A discrete transformation is really one that you can only do sort of a finite number of times. So one nice example was our equilateral triangle being rotated. Actually, we'll just say being rotated through its center. And if I ask, what are the sets of transformations that carry corners of the triangle into corners of the triangle? That means where there was a corner initially, there's a corner afterwards. Okay, well, that means you can do nothing. That's the identity. If you don't touch the triangle, all the corners stay where they were. The corners are still corners. I can rotate it by 120 degrees. Or I can rotate it by 240 degrees. And that is the set. That's what the curly brackets mean. I'm giving you a set of things. Look, there's 3 things there. That's a set. So that's the set of transformations that carry the corners of an equilateral triangle back into the corners. And I'm talking about rotations around the center. And it's clearly discrete. I can't do like a 60-degree rotation because that won't land the corners back where there were corners before. You can clearly rotate a triangle by 60 degrees. But the thing I'm defining is rotations that carry corners into corners. So does everybody agree that that's a discrete set of transformations? Good. All right. This is also an example of a finite transformation. It's something that you have a finite number of transformations available. There are basically 3. Okay. Another set of discrete transformations is to take a line and then discretize it, say into points that are separated by 1 or 1 meter, if you want to be physical. And then talk about translating from one dot to another. Oops. Okay. If you're always going to end on a dot, clearly this is discrete. You can't just move an arbitrarily short distance. You always have to jump just far enough to land on a dot. So it's discrete, but it's infinite if these things go to infinity. So for discrete transformations, I can have cases where I have a finite number of transformations, or I can have a case where I have an infinite number of transformations. Yes?
So rotating like 480 is the same as rotating 180 in this case? Like that's not...
Yeah, so rotations are defined by this periodicity condition that a 360-degree rotation is identical to the identity. So if you tried to write down R360, it's actually the same as this. Now, there's a lot of interesting things we can play around with that. For example, if you ever want to go into the story of spinors, then you realize that rotation by 360 degrees is not the identity, strangely enough. And that's part of the love of spinors, and you should take particle physics to learn that. But for most objects, and the ones we'll deal with in this class, a rotation by 360 degrees is equivalent to the identity. And therefore, anything beyond 360 is always the same as something within the set from 0 to 360. Okay. All right, and then as opposed to discrete, we could talk about continuous transformations. Continuous transformations are necessarily infinite. I mean, if you just think about that, if I have a continuous set of things, I have an infinity of things. Like you could, if I give you the line, you can take a little interval on that line and there's an infinite number of points between those two things. And I can take an even smaller interval and there's an infinite number of points between them. So continuous automatically means infinite. So if I say how many transformations are there in a continuous set of transformations, you say infinity. However, it is actually important to distinguish between two different types of continuous transformations. We can, for example, talk about, for example, the rotations around a circle through some angle theta. And for our normal definition of rotations, we have that the angle goes from 0, so the square bracket means we include 0, up to 2 pi, where the round bracket means we do not include 2 pi. Because if you go to 2 pi, that's exactly 0, and you don't want to do it twice. So we include everything from 0 up to a smidge before 2 pi, but we don't actually allow ourselves to go all the way to 2 pi, because then that's the same as 0. Okay? So that's what the square and the round bracket mean. This is an example of what's called a compact continuous transformation. And the word compact just means that the thing you're using to describe how much you're transforming by, in this case an angle, takes a finite range. Theta goes from 0 to 2 pi. Okay? However, we have another class which is, for example, taking the real line and just translating from one point to another. Now this is not a set of points, this is literally the continuous line. Okay. And I just want to move from one point to another. There's an infinite number of ways I can do that, and there's an infinite number of sizes, of distances I can translate, so this is what's called a non-compact continuous set of transformations. Okay. All right, last but not least is space-time versus internal. So space-time is essentially the following. When we coordinatize space-time, we have a space-time and we lay down a coordinate system, and then we describe things using that coordinate system, a space-time transformation is reflected by picking another set of coordinates, transforming from one set of coordinates to another. And this can be something as simple as rotating your coordinates. It can be the same as translating your coordinates origin, boosting your coordinates. If you don't know what the word boost means, that's okay, we'll define that later. Okay? Special relativity is really interested in space-time transformations. Internal transformations are a little bit weirder, but these generally are transformations on what we call internal spaces. and they do not impact space-time. We're not going to talk about these in this class, but they play a central role in particle physics. In particle physics, the symmetries and the transformations you study are transformations in these internal, what are called isospaces, things like color space, flavor space. And you can do rotations in those spaces that have nothing to do with rotating in space-time. Okay? So, I mean, I'm throwing down some definitions, but we're going to spend every bit of time in this course talking about space-time transformations. Yes, sir?
What's the difference between compact and finite and then non-compact? Are they specifically like finite and infinite, or is it discrete case?
So the words compact and non-compact here are referring to the range over which, so it's like saying the difference between the infinite line and the line segment. If I ask you how many points are in each of these, the answer is infinite, right? There's an infinite number of points here, there's an infinite number of points here. This is something we would call non-compact, and this is compact. Compact essentially means you can draw bars around the edges of it. It lives within a certain range, even though it's infinite. Okay, non-compact means this, that it's infinite and you can't put bounds around it. And I think that's borne out in these examples. Okay, so I floated a lot of words at, oh, another question?
Sorry, but I can't read the space-time definition you have up there.
Oh, that's because it's written with very terrible handwriting. And the good news, of course, is so when we coordinate, it's because I made up a new word. That is short. You can read it. It just didn't make it damn like a sentence. When we coordinatize space-time, or coordinate time, I like that. Let's make that a new word. Hey man, you in a coordinate time?
Oh yeah, coordinate time. Coordinate time.
Coordinate time. That's good. Even that's being abbreviated. But when we coordinatize space-time, space-time transformations are induced by changing the coordinates we're using. And we're going to get a really thorough mathematical understanding of why I have to talk about coordinates in this story. Okay. But what I was going to say was, if you can't read something later on, just look at the notes on the website, and everything is actually written reasonably clearly in the notes. But you can always ask me for clarification. I said there were no questions today. You broke the rules. I put 10 copies of your card in your deck. All right.
Whoa, you've been asking us questions.
I'm kidding. I'm just pulling your leg. Okay, so any questions about these sorts of definitions? So we are going to invariably throughout the course kind of touch on examples of all of these. I'm going to spend a lot of time talking about discrete things because they're just sort of easier to tame. You know, I can write down all of them sometimes if I'm lucky. But our ultimate aim, to be completely honest, is to look at continuous transformations, both compact and non-compact continuous transformations. We're going to have sets of both of these that we're going to be our focus. Okay, so now is where we get mathy. And the wonderful thing is that you're going to hear a lot of words here that even if you haven't studied them properly, you know they exist. And now is when we get to actually put them down concretely. Some of you might have been lucky enough to actually study them. So our focus, and the focus most often in physics when you're talking about transformations, are ones that form groups, which of course looks like a perfectly innocuous word in the common vernacular, but has a very precise mathematical meaning. And more importantly, perhaps, is that associated with those groups are these things called representations of the groups. And so let's get a formal definition of these two things down before we go any further. So without any further ado, what is a group? A group, which I will call G, is a collection of, and in this case, a group could actually be a collection of many different things, but since we're talking about transformations, I'm going to talk about a group of transformations. So a group G is a collection of transformations. And I'll just label those like some by some letters, dot, 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 dot. So the whole of these is the group G. People get bothered by this. Is this one of them or is this all of them? Well, G, big G is like Nancy's 4th grade class. And then Timmy is one of the students in Nancy's 4th grade class. Just made that up on the fly. Pretty good, right? Okay, so proud of myself. So right now I've just got a set. Like this is literally just, here's some stuff. Boom. That's not very interesting mathematically. So what we're going to do is we're going to combine this with a composition, which we will because we're artistically challenged, represent by a dot, that satisfies some very important axioms. 1, closure. And I'm going to give you an example of what I mean by each of these statements. If A and B, let me be a little bit more concise. If A and B, there it is, there's that funny symbol. What does it mean? Are elements of G. So when I write that, I'm just saying are elements of the set G. Then, that's what the right arrow means. Then A composed with B must also be an element of G. Oh man, I'm going to say it anyway. Don't be offended. No, I'm not going to say it. Maybe you can say it.
You can't.
Okay, so, no, it's horrible. It's actually, oh my God, I can't possibly say it. No, I can't say it. I can't say it. I will say it to you after class, off camera.
Read it, you're cool.
What?
Did you write it on the paper?
No, it's not on the paper. It's Nancy's 4th grade class and sex. Go in there. It's no.
I can say it if you don't want.
No. It's an example that I used to use about like conserved and constant quantities in physics 1, and it was like college age people, which is still not good for me to talk about, but at least it's age appropriate for 4th grade. Okay, so let me. Yes, go ahead.
What's the operators between A and B?
Thank you. Thank you for asking. I thought you were going back to Nancy's classroom. This was going to be sex, but here it's literally the answer to that question is different from group to group to group. There is no straightforward, in all cases, it's multiplication or addition or whatever. That's why I use this hoity-toity word, composition. The word composition means to put two things together. And then when I define the group for you, I have to tell you exactly what that rule is. So right now it's just a dot. In some cases it might be addition. In some cases it might be subtraction. Not really subtraction for group. Addition, multiplication, matrix multiplication, lots of different
I
possibilities.
forgot that we were talking about the composition itself. So.
Yeah, okay. So I'm just going to do this in the case of this class. If this class were formed of a group and dot was procreation between members of the class, if two of you procreate, you create another individual, but that individual is not part of the original group. So that fails closure. Two of you procreate, the person that you make is not in this class.
Yeah.
So that does not close. So closure means two things combined have to give you back something else that's already in the set. And this is a property of almost every set of transformations you can imagine. And we'll look at lots and lots of examples and show you that they satisfy this. God, I'm going to get fired. Okay. At the very least, people are going to be like, I'm not sending my child to the school of mines. They're terrible there. There is some identity. There is some element. I'm just going to call it I. A lot of people like to call it E, lowercase e, but I just find that annoying. There is some element on the group I, so I is on G, such that If I compose the identity with any element on the group, I get back the element of the group for any A on G. Okay? And this is just a formal statement of what you've known of as the identity in many different contexts. Like in multiplication, the identity is just the number 1. I can take any number, multiply by 1, I get the same number. Okay. But the identity can be different in different contexts. What's the identity in addition?
0.
It's 0. Okay. So a lot of times we'll represent the identity by 1 or I, but it can actually take on different values depending on what kind of set of transformations you're considering. Okay? Third property is inverse. If I take any element of the group, then there exists another element on the group that we call A inverse, such that A inverse equals the identity. It's kind of what you naturally think of as the inverse. You combine it with the original thing and you get back the number 1 if you're talking about multiplication, 0 if you're talking about addition. Generically, you combine it with its inverse and you get back the identity. It's important that inverse has to be an element of the group. Okay? So just to give you a very, very quick example, if I talk about addition of positive integers, does that form a group? No, right? Because the inverses don't exist. What's the inverse of 1? Negative 1, but that's not on the positive integers. And then last but not least is our best friend, associativity. And this is exactly what you've seen for associativity ever since you were a wee child, screaming from your mother's belly. Or whenever you learn about associativity, I don't know. And that's if you change the order of operation of a composition of 3 things, then you get the same result. Okay? Associativity is one that actually almost everything we think of satisfies. It's hard to find things that are non-associative. Okay? Now you can relax conditions and then you get structures which are more general than groups. And so I think if you relax associativity, I think it's if you relax associativity, then you get these things called groupoids, which are interesting in their own right. But for most part in physics, we have all 4 of these true simultaneously, so we're working with groups. Now, you might have noticed one operation which we often see in our first introduction to mathematics, which does not present itself in these definitions, and that is commutativity, right? And that's because it turns out that many, many groups of interest in physics do not commute. Okay? So commutativity, which is just the order in which you do things, is not required of a group. If the group is commutative, if it turns out that you can do the composition in any order and get the same answer, then the group is called abelian. So we have abelian and non-abelian because commutative and non-commutative just wouldn't make sense. I'm sure there's a perfectly good reason for calling them abelian and non-abelian, but they mean commutative and non-commutative in the context of groups. Okay? And then the last thing that I will say before we move on to more sophisticated things is that anytime we have a set, one thing you might ask is, well, what if we take a subset? You know, what if we take Nancy's 4th grade classroom and just look at the boys? Forget about the girls. And you could ask, does the subset form a group? Okay? So what we find is, if a subset of G satisfies 1 through 4, that's these 4 criteria, then it forms a group. But it's a special name, it's called a subgroup. Okay? Pop quiz. Jonathan. If all of the boys in Nancy's 4th grade classroom formed a subgroup of Nancy's 4th grade classroom, could the girls possibly form a subgroup?
Yes.
Who must be included in the boys? The identity. But then would the identity be included in the girls? No. I know, it's a tough one. You're thinking like fourth graders. What do they look like? Okay, just don't think too hard about it. Yeah.
So if, so that.
By the way, the identity is unique. So, but carry
So
on.
is the identity of the teacher.
So, so a group can't have like, can a group have different subgroups that would all include the identity?
Yes. So a group can have multiple subgroups, but they have to all
Okay,
share
it's
the
just that
identity.
specific example.
Yeah.
Okay, yeah.
Can you ever have a group with like 2 unique identities?
Two unique, no. Yeah.
Is it important that you wrote AA inverse, or could you have also written?
Sorry, so that's the one, well, I want to be a little bit careful. So in all the examples that we're going to talk about, you can do AA inverse or you can do A inverse A, and those pairs are always going to commute. There are situations where you have to be very careful, and it depends on the kind of action that you're doing, where you might define what's called a left inverse versus a right inverse, and those can actually be distinct. But we're not going to encounter any of those cases in this class. So, all right. Other questions? Just roll it. Roll it. Got it. 4 more pages, 15 minutes. Screwed. All right. Okay. So, raise your hand if you have seen the definitions of a group before. Sweet. Where have you seen them?
It's particle.
Oh, in particle. Of course, I wasn't talking to you. Anybody else?
Cryptography.
Cryptography. Nice. Anybody else?
I just had a really cool 7th grade teacher.
7th grade teacher. I want your 7th. I don't want your 7th grade. I know, but
Linear algebra.
linear algebra. Okay.
Oh, yeah, we did actually.
Oh yeah. Oh yeah. Okay. Well, even if you've heard of groups, you might not have heard so much about representations. So let's talk about representations. We can often abstractly define a group. For example, I can say we're going to consider 2 dimensions, rotations in 2 dimensions, where the composition rule for our group is that we add the rotation angles. So the set of elements is all the rotations in 2 dimensions, and then when you want to combine 2 rotations, that's the composition, you just take the angle from the first, the angle from the second, and you add the angles together. So that's sort of an abstract way to define a group. But often in physics, and to make things concrete, we instead think about what are called the representations of the group. So that is, how does the group act on things? These are what are called representations. So you might remember, I talked about the triangle, and then I talked about rotations, and the set of rotations in particular that take the corners into the corners. Okay? I can talk about these 3 things without ever referring to a triangle. I can just say rotation by nothing, rotation by 120, rotation by 240. And that forms a group. And I can talk about how do you combine these. If I combine these, I times R120, well, it's R120 because this is the identity. This has an inverse. What's the inverse of this?
240.
It's R240, because if I take this and combine it with that, I get the identity. Satisfies all the axioms of group. Okay? But it's easier to swallow when I say, let's think about these in terms of this triangle. So we often use representations to make thinking about groups concrete, but it turns out when we do physics and we actually write down equations, we are actually writing down things in representations of groups. So we're rarely working with groups in the abstract, we're really talking about groups and representations of those groups. And when we talk about representations of groups, what we discover is that a single group can have many different representations. You can represent a group in many different ways. some of which are gooder than others. And if you don't know that word, I'm bringing it back. Taking it back from the redheads. All right. So in particular, kind of the best thing that we can do is find what are called faithful representations. Faithful representations are awesome because they give us all of the information we could want to know about the group. On the other hand, unfaithful representations, well, they're not faithful. They don't tell us everything. So let me give you a very, very quick example of faithful versus unfaithful representations of a group. So the group I'm going to talk about, and people from particle physics are going to laugh because they know this one very well, is the set of rotations in a plane by 90 degrees with the usual composition of rotations. That is, if I rotate by 90 and then I want to do another rotation by 90, I'm thinking of a rotation by 90 plus 90, which is 180. I add the angles to compose two rotations. Notice, I say that and you might be like, well, you always add the angles when you do rotations. No, you don't. Like if I take a rotation around the x-axis by 90 and a rotation around the y-axis by 90, that is not equivalent to a rotation by 180. Because like, what axis? So just because I'm talking about rotations doesn't mean we always add the angle. But rotations in 2 dimensions, you do legitimately just add the angles. Are we all on board with that? Okay. We find when we talk about things formally mathematically, we often have to make statements very, very clear, which we have just understood so well for so long that we never even maybe said them out loud to ourselves. But we have to say them, especially when we're going to look at more complicated examples. So everybody understands what I'm talking about when I say rotations in a plane by 90? Okay. And now I'm going to look at various representations. So the first representation, which I'll call R1, I can imagine as a square. And then what I'm going to do is I'm going to label the corners of the square with letters A, B, C, and D. And I would argue to you that this is a faithful representation of this transformation, because what I can do is I can do nothing and it looks like this. I can rotate it by 90 and that will change the way it looks. Which means that this shape tells me that I have rotated by 90. You know what's going to happen, the letters are all going to move. And then I can rotate by, instead of 90, 180, and this square will tell me that. And then lastly, I can rotate by 240, and the square will tell me that. So in this representation, the elements of this group look like this. There are 4 of them. And of course, if we go to 360, we go back to the identity. Okay. But now let's consider a slightly different representation. Consider a representation where we take a square and we label the corners like that. You notice I can do nothing. I can rotate it by 90 and that will definitely look different. But beyond that, I get back to where I started. Because if I rotate this thing by 180, it just looks the same as I started. So this representation is not a faithful representation of this set. Because some of the elements of the set of transformations, they don't really give you something that you can identify. It's what we often call degenerate, because what we find is that the identity from this set is going to the identity, but also 180 is going to the identity. R90 is going to R90, but also R240 is going. Degenerate means you've got more than one thing trying to act like the same thing. Okay? Yes?
So is degeneracy always a test of whether or not a faithful representation?
Yeah, degeneracy is always going to be a feature of unfaithful representations. Okay. And non-degeneracy basically the definition of a faithful representation. And then last but not least, we have what we call the identity representation, where everything is represented by the identity. Because no matter how much you rotate through any of those four, it looks the same after every one. And that is, of course, supremely degenerate. Okay? Now, these might look weird. Like you might say, this is the only thing you should ever use, because God damn it, I want to know what all different elements of the group are, and I want to know, you know, blah, 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 blah. Who would ever use this? Say it. I heard somebody say it. What's an example of the identity representation that we encounter a lot? I thought I heard somebody say it. That's what a scalar is. A scalar is the identity representation of the rotation group. You can rotate all you want, and the scalar doesn't change. It's like you're just applying the identity every time. Okay? Okay, so I will endeavor to get through this last page, and then I won't keep you late. All right. So, thus far, things have been kind of picture-y. Take the square, rotate the triangle. We're still like, I can't write down an equation with shapes. You know, let's get some stuff that we can use equations to work with. And so, in order to do this, we have to go one more level of sophistication, but actually just taking you to something that you have been working with for a very, very long time. And that is we often work with representations where the transformations are linear operators represented by matrices. Okay. And in fact, in much of what you've done to transform things in your other classes, you've probably used matrices in order to do that. So for example, when you wanted to describe rotations of coordinate systems, you wrote down a rotation matrix. Okay. When we talked about transformations in particle physics, we wrote down SU2 matrices, SU3 matrices, etc. This is just a representation. Okay. So let me actually give you a concrete example of how this mapping could work. So if I'm talking about the group that was over here, that's the set of rotations by 90 degrees in a plane, okay? Then what we can do is we can take a representation, say the faithful one, and I'm going to start by drawing the pictures, and then once I've got the machinery down, we can get rid of the pictures. Okay, so this is my faithful representation. And what I'm going to do is I'm just going to, instead of drawing a square with letters, I'm just going to write down a matrix that describes that. And I can pick any matrix I want, but after this starting point, I have to be a little bit careful in how I proceed. So the matrix that I'm going to write down is going to be a column matrix. Some people like to use the word vector. That's fine. You can say vector, but we're going to kind of talk about vectors in a slightly different context. And then based on this, I can look at the other configurations that I could eventually reach and assign them labels. And just to keep my life easy, I'll just let the one migrate down. So filling out with 4 possibilities is going to give me something like this. Okay. And now what do I need? Now, say it again.
A composition rule?
Well, I haven't even given you the transformation theory. Right now, I've just drawn analogs of these things. Transformations are what take you from one of these to the next. So a transformation takes you from this to this, or from this to this, or from this to this, okay? So I want to write down the transformations, and then I'll tell you the composition rule. So if I stare really carefully at this, and actually I study all of them, I can, after staring long enough, realize that the transformation, I'll do one if you guys will do the others. I'll do one. The transformation that corresponds to doing nothing is represented by this matrix. Okay? Because if I take this matrix and I multiply this column matrix using just the good old rules of matrix multiplication, you all know what the identity matrix does. It just gives you back the thing you started with. And you can do it on this, on this, on this, or on this, and you get back the same thing. Okay? I did my job. Okay. You guys are not team players. Okay, so now a less trivial case is to say, all right, well, what matrix would actually represent a 90-degree rotation? So what matrix can I use on this that would give me back this? But remember, it also has to take this and give me this, take this and give me this, and take this and give me back this.
Try that.
Yeah, I'll just write it down. You guys can figure it out if you took long enough. I mean, it's not impossible or beyond you. But here is the bad boy that does it. And then just to fill out the rest so that you have them for your viewing pleasure.
I have a quick question.
Yeah.
What's 180 plus 90?
Oh, shit. Yeah. Where was I getting 40 from?
You're getting 240 from it.
I was getting 240 from the triangle. Yeah. This is the hyper triangular rectangular square triangle layer, square triangle. Yes, thank you for correcting that. Okay, now I want to be really careful because right now, what I have given you is basically labels for these things that I'm going to transform, and then these are the transformations. Okay? Now, this is a set, and this is a set. Which of those two sets do you think might form a group? The second one, okay? But what do we need to provide in order to make this a group? It has to be a set of things with a composition. So I have to give you a rule for how to combine these. Well, what do you think our rule is going to be? Matrix multiplication. So if I want to combine I with R90, I literally take this matrix and multiply this matrix. The same with this and this. Okay? So our group in this case can be, now notice, what was the group I started with? The group I started with was rotations by 90 degrees in a plane where the composition rule was that you add the angles. Okay? Here I have a faithful representation of that group in terms of four matrices where the composition rule is reflected by matrix multiplication. This is something we can write equations with. We can write matrix equations, and we do. All right? And notice the matrix, and you can sit and work it out with these matrices. It doesn't take long to multiply them. but they do exactly what you think they do. If I take this matrix and I multiply it by this matrix, what do you think I get? I get this matrix. If I take this matrix and square it, what do you think I get? I get this matrix. Okay. It does exactly what you expect it to do based on adding angles. You know, if you do this one twice, you're going to get this one because 90 plus 90 is 180. All of that information is encoded in these particular matrices. Okay? And these matrices are not unique. They happen to have been built from these choices. But I could have picked different choices. You know, I could have picked this one to be 0, 1, 1, 0, and then gave these different labels. Or I could have, for example, called this 1, minus 1, 0, 0, and then used a 1, minus 1, and a 1, minus 1, and a 1, minus 1, and then these matrices would have more non-zeros, and some of them would have negatives. You know what else? I didn't actually have to use 4-component vectors, or 4-component column matrices. I could have made do with smaller ones. What's the smallest you think I could get away with? 1. I could have actually encoded all of this in a single number, albeit it has to be complex. Okay? But that's something you're going to get to explore in your homework. All right, that's it for today. If you want to hang around and ask me questions, I'll be here until 7. Oh, I want to say this because I was going to say it earlier, and I want to make sure I say it. Especially for anyone who hasn't seen this kind of stuff before. So this class, for most people, is like this, and then it gets easier. There's just so many new ideas, so much new language that you have to get used to. Just wait till we get to index notation. So there's a very steep learning curve at the beginning. I had a senior design student 3 years ago who I developed a set of online tutorials over exactly this material. And they are on my course website at the bottom. There's 6 videos. They're probably about 17 minutes long each. There's places where you pause and work out a little problem. And it covers exactly this material in beautiful detail. Okay? So if you feel yourself struggling with this material, by all means make use of those tutorials. In fact, even if you already feel comfortable, make use of those tutorials because there's various little quizzes that will let you check whether you actually know it as well as you think. Okay? All right, that's it for today. I will return.